All right, how's it going, everybody? We are here on day 2 of week 1. Today we're going to talk about section 6.2, our right triangle trigonometry. Last class we talked a decent chunk about circles. Today we're going to talk a decent chunk about right triangles. We're going to spend a pretty significant amount of time this semester discussing only right triangles before we move on to non-right triangles, also known as oblique triangles. And what we're going to end up seeing once we get out to those non-right triangles, that a lot of our analysis of those types of triangles is really going to stem from us just forcing those triangles to seem like right triangles and continuing on with our analysis that we've learned in this chapter here. So we're going to spend a lot of time with right triangles. We're going to introduce a lot of that stuff today here. So today we're going to define kind of a lot of things here, but these are all of these definitions that we're going to need to be using for pretty much every day for the rest of the semester here. So a lot of important stuff here today. None of it itself is too difficult, except for perhaps simply just the volume of new definitions here. So do feel free to pause this when you need to, kind of make your own lists of reference information right here. You should have notes that you've taken that are things that you can glance at more quickly rather than having to watch a video or read a paragraph. Making that reference information for yourself for quick lookups is going to be very valuable for you. So today, the two primary things we're going to do is we're first going to look at how do we measure side lengths of right triangles. Then we're going to look at the relationships between those side lengths after we've determined how to measure them. But before we do that, we want to kind of get some general notation for how you should expect to look at right triangles this semester and some sort of like names for some things here. So when I say notation for right triangles, let's just draw one here. Um, so in general, as we said before, right triangle is typically denoted by the square, indicating that that is intended to be a 90-degree angle. This is just helpful since most people are bad at drawing, and so I don't care if you draw something that's actually a perfect right angle. If I see a box in the corner, I know that that is you telling me that's a right angle right there. In general, we want to be labeling all of our side lengths here with relative consistency here. So a typical usage for labeling the side lengths is to do lowercase letters A, B, and C. We're going to later use some capital letters A, B, and C to indicate some angles. So if you're following this convention, lowercase is sort of a specific part of it here. In general, we refer to these two guys right here, each as legs, the A and the B right here. And the diagonal one that is opposite of the right angle is what we refer to as the hypotenuse. It's a very weird word right there. I feel like typically I talk about like where words come from. Not sure on this one. Hypotenuse, sort of strange word. So we have two legs and a hypotenuse on every right triangle here. In general, it's also typically the case that we label the associated interior angles here. We know that this is a 90-degree angle, but these two are of some unknown measure right here. So we saw in the last video using this theta, like an O with a line through it horizontally. The other Greek letter that we often use to denote angles is a phi, which is also a circle and a straight line, but here the straight line is vertical. So this guy is theta. And this guy here is phi right there. Both Greek letters. And those are just typically used to denote angles. I very rarely see those two Greek letters used to indicate anything other than the angle associated with like a geometric shape right there, or the angle between two lines or something like that. So theta and phi, you're going to see a ton of those this semester. Pretty typical when we're talking about right triangles. Later, when we move on to oblique triangles, that's when we'll be using lowercase ABC for the side lengths and capital ABC for the three angles. But in right triangles, since one of the angles is always known, we typically use theta and phi as our other two angles that are in there. So this is like my most generic right triangle right here. Three unknown side lengths, which we use lowercase letters, two unknown interior angles, which we typically use Greek letters, theta and phi, to denote right there. So one of the things that we're going to want to be able to do here is say, if we know two legs of a triangle, we want to be able to identify a third, and we're going to have some help from that from the Pythagorean theorem. I'm sure this is something that most of us are at least vaguely familiar with, although I'm also quite certain that most of us have never seen where the Pythagorean theorem comes from. Two things I'd like to say about this. One, the Pythagorean theorem has been known for thousands and thousands of years. I'm talking like somewhere around like 4, 5, 6,000 years we've been familiar with the Pythagorean theorem. Another thing that I'd like to point out is that there absolutely is a dude whose name was Pythagoras. This theorem is absolutely named after him, and it is absolutely not the case that he is actually the one that came up with this. One, we know that people in other cultures came up with this before he did. Two, Pythagoras was actually a guy that sort of like ran a school, and it is very commonly believed that it's actually one of his students that deduced this. And as it honestly still kind of goes in modern academia today, if you want an idea to sort of gain traction, it doesn't help to stick some random dude's name on it. Helping attach it to a slightly more famous or more well-known person is a way to help get that idea spread around. So it is generally believed by mathematical historians that it is more likely a student of Pythagoras who this should actually be attributed to, but it became to be known as his theorem for whatever sort of bad reasons that exist for types of things like that in academia today. Pythagoras was actually sort of a crazy person running a cult more than like an academic running an academic institution, but still an interesting character to read about in history. So you should go check out some more stuff about Pythagoras if you care about that. But the bottom line is that dealing with right triangles has been some of like the earliest math that all civilizations have ever done. The Pythagorean theorem has to probably be one of the most proved theorems in the history of math, I'd have to guess. There are literally hundreds of known ways that you can prove the relationship that we're about to establish right here. So rather than me just telling you the Pythagorean theorem, let's go ahead and draw a geometric diagram that's going to show us this relationship right here. So this is I think, in my mind, the easiest geometric proof that I've seen. I could be convinced that there's probably something maybe easier out there, only because of the sheer number of different proofs of this relationship that there is. But let's go ahead and look at one way that we can show this. So what I'm going to do is I'm going to draw a square. And inside of the square, I'm going to draw another figure here. And what I'm going to do is I'm going to draw, so notice I'm sectioning off like a right triangle right here. What I want to do is section off this exact same right triangle once on each of the four sides. So this triangle right here is exactly the same as this triangle, just sort of like rotated, right? This triangle here, the exact same triangle, and this triangle here is also the exact same triangle. So I'm going to label all these values right here. And very importantly, notice that what I just did is I just created four right triangles here. All right. I'm going to give some labels to each of these guys right here. I'm going to label the short leg of each triangle to be A and the long leg to be B. All right, so those four are identical. And finally, I'm going to go ahead and call this hypotenuse, sort of the thing we typically call it, which is C. And what we're going to do here is we are going to come up with two different ways to describe the area of the entire square, right? The entire square. We're going to come up with two different ways to state its area. So I'm going to say the area of the big square right there. I want to come up with two different ways to write it. One way that I can see that I could compute the area of this entire square is to recognize that one side length here seems to be a plus b units long. And we know to find the area of a square, you can square its side length right there, right? A plus b times a plus b will give us this overall area right here. So one way that I could write the area of a square, of this square, is a plus b squared. And if we do a little bit of algebra here, if we square out this quadratic right here, we'll get a squared plus 2ab plus b squared if we FOIL that guy out right there. So this is one way that I can come up with an expression for the total area of this entire shape. Let's come up with a second way that we can express the area of this entire shape. Another thing that I could do is, rather than using this side length on the outside of a plus b, we could individually add up the area of each of the five shapes that we see right here. That would give us also the entire area of the whole square, right? So here what I would be getting is the interior part looks like it's just c squared, so that gets us the middle square, plus it looks like we're going to get four triangles areas, right? Four copies of this triangle right here is also what we're adding up. The area of a triangle is 1/2 times base times height. Here my base is A, my height is B. So 1/2 base times height, right? So this is the area, in parentheses here, that's the area of one triangle. That's the area of the interior square. And if we add 4 triangles in the interior square, it gets us the entire area. So what I'm claiming to you is that both this expression and this expression have to be the same thing as each other because they both represent the area of the entire square, right? So let's go ahead and by the way, this looks like this simplifies a little bit to c squared plus 2ab, right? 4 times 1/2 is 2. So let's go ahead and set these equal to each other now and see what we find. The area of the square, the area of the square, one version, should be equal to the other version of the area of a square. So this says to me a squared plus 2ab plus b squared should be equal to c squared plus 2ab. Well, I'm just going to subtract 2ab from both sides and look what we're left with. A squared plus b squared equals c squared, where a and b were the two legs of the right triangles, and A and B were the legs, and C is the hypotenuse there, right? So this is the Pythagorean theorem, and it can come from just drawing that image and coming up with two different ways to represent the area and setting those two area equations. They must be equal since they both represent the area of the same shape. Setting them equal to each other can show us this relationship between these terms A, B, and C. So again, the Pythagorean theorem, super important. You'll use it all over the place this semester. And it is always saying it must be the leg squared plus the other leg squared equals the hypotenuse squared. And it matters. So notice, by the way, that A and B are sort of interchangeable. A and B are both legs. C has to be the hypotenuse. You can't just mix and match all of A, B, and C. A and B are interchangeable, but not C. Got to be the hypotenuse for C. So as examples, let's go ahead and find the missing side lengths. And by the way, this will be a thing that I'm going to end up doing a bunch this semester. I should just say, in some of the other online classes I've been teaching have been less about drawing pictures, or they have been about drawing pictures that I can easily draw with like a graphing utility. This semester we're going to draw tons of triangles and circles, which it's just a little bit more inconvenient for me to like go make a nice triangle for every single one of these right here. So as you'll see in my notes, as I've arbitrarily decided right here, these purple things are sort of my pre-written stuff. Everything that I write in black will be sort of like the notes that are associated with them. So as examples, let's go ahead and find the missing side lengths that are associated with these 4 right triangles right here. And I guess if I'm being appropriate right here, I still need this guy is missing its little box down there. So let's go ahead and use the Pythagorean theorem for each of these guys. So remembering that our Pythagorean theorem is a squared plus b squared equals c squared, our job is to identify what is the missing side. In this case right here, it seems like c is the missing side, right, our hypotenuse. So it looks like I can make the statement that says 3 squared plus 4 squared equals c squared. I want to know what is c. This looks like 9 plus 16 equals c squared. 9 plus 16 is 25. And so I now can take the square root on both sides, and that will help me identify. Let me give myself a smidge more room right here. To help me identify that c must be the square root of 25, which must be 5. Right? So I have now identified that c must be equal to 5 in this case right here. A 3, 4, 5 triangle turns out to be the smallest side lengths that we can ever have, where all the side lengths are whole numbers in any right triangle. A 3, 4, 5 triangle is like literally the name of this guy that's right here, and we'll come back to see it a few more times this semester for other purposes that are out there. One last little technicality I want to say right here. I'm hoping that there's a handful of people that have enough algebra wherewithal to notice that in general here, the more general solution to this is that c could either be positive or negative 5, right? Negative 5 squared, negative 5 times negative 5, also positive 25. If you're in algebra class and I tell you to solve this equation, you'd better give me 2 answers, positive and negative 5. In this case, however, we're looking to measure a distance, and we're never going to measure a hypotenuse distance as a negative number, although I will say we will come to look at some of these guys as having positive versus negative lengths for the legs. The hypotenuse is always a distance between 2 points, and that distance will always be represented as a positive number. So in this case, I'm only interested in that positive solution right there. We can do a few more of these, right? So I can see here again, similar situation. This looks like my A and B. Again, it looks like the hypotenuse is the unknown. So I can do my 5 squared plus 2 squared equals c squared. It looks like I'm getting 25 plus 4 equals c squared. And that's going to give me 29 equals c squared. Well, in our previous example, 25 was a nice number. It's a perfect square. So square rooting it had a nice clean answer right here. For this one, we don't really get that. So all we're going to do is just say, yep, it's the square root of 29. You could certainly go to your calculator and get a decimal for that. Most of the time, I won't be interested in that this semester. In most of the cases where I'm asking you questions and where My Open Math is asking you questions, we're much more often interested in the exact answer. And here the exact answer is square root 29, and that's exactly how I'm going to leave this guy right here. This next one is an important one. I'm doing this third example right here because it is sort of a special case triangle right here. We'll see this guy come up again in the next couple lectures here. It's about as easy as I can get, right? The nicest number ever to do math with, aside from 0, is 1. Again, it looks like the hypotenuse is missing, which is why this is big time a repeater here. Nothing super exciting mathematically is going to happen here, but this triangle is special in that the side lengths here, the legs, I should say, are exactly the same length. This is really just 1 plus 1 equals c squared, 2 equals c squared, and that's going to tell me that c is apparently the square root of 2. Right. So relatively easy one there, but this 1, 1, root 2 triangle, it's one of our slightly more special than the others right triangle, and we'll come back to talk about what makes that guy special here in the next couple sections here. Finally, you should notice that in all three of the examples that I've done so far, c has been the unknown thing, the hypotenuse has been the unknown thing. That's not necessarily going to be the case. That's just the case in which it's kind of the easiest to do our math. Let's look at least one example right here where that's not the case. So notice here, this means that one of our legs is missing. It doesn't matter if you call this missing leg A or B. It really doesn't. I'm going to call it B just because it doesn't matter right there. A and B are always interchangeable. C is not. So it looks like what I know now is that 7 squared plus b squared is equal to 25 squared. So I'm going to have to actually do a little bit of algebra here for this guy, but it's not going to be too crazy. And so it looks like I'm looking at 49 plus b squared equals, I can go to my calculator, check out my 25 squared here, and I'm seeing 625. I want to solve for b, so let's go ahead and do a little bit of the algebra right here. I'm going to subtract 49 from both sides. I'm going to use my calculator to help me out with that. 625 minus 49, I'm seeing a 576. And it looks to me like what we should be finding for b is the square root of 576. For all these big ones out here, it's worth double checking. I'm not really interested in a decimal answer, but when I go to my calculator, what I'm finding is that this actually turns out to be a very clean number right there. That one is exactly 24. So it looks like we've identified that b is going to be 24 in this case right there, right? If it hadn't come out to a clean number, if there was any decimals, I would prefer it just to be left in the square root form right there. Hey, Suyesh, what's going on? This is college trigonometry right here. We're just getting our semester started. So using the Pythagorean theorem, if we ever know any two side lengths, we can always go ahead and find the third, solving for it using our Pythagorean theorem equation right here. And again, this will be something that follows us all semester. We're going to regularly want to use some pieces of information about a triangle to find additional pieces of information. We got to be able to do a little bit of solving. And remember, I like exact answers. Leave those square root answers alone. If otherwise, that would be a decimal. But if they do reduce nicely, we can go ahead and simplify them to the whole number constant that we're getting there. In general, to solve a triangle is to do a little bit more than this. When we say to solve a triangle, what we mean is you want to find not only all three side lengths, but also all three angles. And notice in our previous examples, we had no angle in, okay, that's not true. We had one of the three angles, but we certainly don't have any necessary way to directly get at what must those other angles be there, right? So to solve a triangle is to find three sides and three angles. It's all of the information surrounding that triangle. And so the question that we should ask ourselves is this. If you know all three side lengths of a right triangle, do you know everything about that triangle? Is it possible for us to have solved the triangle completely? And I'm going to give you a soft answer on this one right now. It's going to turn out that the answer to this is yes, but not until the end of chapter 7. All right, well, this one's going to take us a while to get a couple more tools that we need. But what we are going to find in about a month from now is that we can take, only knowing the side lengths, we can use those to determine what the angles must be within a triangle. So the answer to this is yes, but not yet. All right. The second question that I'm asking here is, if you know all three angles of a right triangle, is it possible that we can solve for all of the information about a triangle? This one's a little bit different here, right? If you know all three angles that are associated with any given triangle, can you determine what the side lengths are? And here, I'm going to suggest to you that the answer to this should be no. And the reason why is because we can scale triangles up or down to be larger or smaller while still maintaining all of the original angle measurements in there. Right? Ooh, I don't have the right, right, this one I have to write it by hand. No. Triangle size can be scaled up or down. While maintaining angle measurements. Right? I could make a triangle that has 30 degrees, 60 degrees, and 90 degrees as my three angles. I could make one that's tiny. I could make one that's massive, right? So knowing the angles doesn't necessarily tell us what our side lengths must be, right? But we've got some definition that's associated with it. Two triangles are similar if all three angles are equal to each other. All right, so I can draw two similar triangles here. I'll give two examples. If my side lengths are 1 and 2, hey, by the way, maybe you can do a little Pythagorean theorem in your head here. 1 squared is 1, 2 squared is 4, 1 plus 4 is 5, and that must be our hypotenuse squared. So it looks like this must be the square root of 5. All right. We've got some theta and we've got some phi in here, and we know that this is a right angle because we're only talking right triangles here. And what we're going to end up seeing here is that we could scale this guy up, right? I could do basically the same triangle, but bigger. I can maintain that this is a right angle. I can maintain that this is theta. I can maintain that this is phi. And what we're going to end up seeing is that we could just scale up all of these side lengths to continue to agree with theta and phi. For example, 2 and 4, well, 2 squared is 4, 4 squared is 16. This would be giving me the square root of 20. And by the way, let's do a little bit of math right here. Square root of 20, I can rewrite this as the square root of 4 times 5, or the square root of 4 times the square root of 5. And that allows me to rewrite this as 2 root 5. Right? And so notice in this similar triangle right here, we have maintained our ratios of side lengths. Right? 2 over 1 is 2. 4 over 2 is 2. Root 5 over 1 is root 5. 2 root 5 over 2. The 2's would cancel, leaving you with just root 5 again. So all of our ratios of side lengths have been maintained, right? And that's really important for us here. So side lengths have changed. But the ratios between side lengths has not. Right? And again, I could do math over here like the hypotenuse divided by the vertical leg. Root 5 over 2, and that's going to be equal to 2 root 5 over 4, because that would simplify down to root 5 over 2 again, right? So even though I have scaled up this triangle in size, if I divide any two consistent side lengths of the triangle, it doesn't matter if it's a big version or a small version, that ratio of side lengths will be maintained in between any two similar triangles right there. So here's kind of the bottom line. If you know the three angles associated with a triangle, it will not tell us what the side lengths are, but it will tell us what the ratios of the side lengths are. All right, and that's valuable information for us. That's still going to be really helpful. It would be kind of nice if just knowing the angles told us the sides. It doesn't, but it does give us some information, the ratio of the side lengths out there at least. We want to identify what those ratios are. In fact, those are going to come to be some of our most important things this entire semester right here. These side length ratios are exactly how we define the trigonometric functions that we're going to study for this entire semester here, right? So what we want to do is let's name all these possible ratios. And again, before we go do it, I want to kind of show you guys what we're looking at here. When I say naming the ratios, I mean 1 divided by 2, 1 divided by root 5, root 5 divided by 2, root 5 divided by 1, 2 divided by 1, 2 divided by root 5. It looks like because there's 3 different lengths, there's 6 different comparisons that we could make between those guys that are right there, right? We want to name all of those ratios right there. So let's go ahead and do that. So given the general right triangle here, right, this is the general one that I drew a minute ago, we're going to define, we've got kind of these 6 words for ourselves here: sine, cosine, tangent, cosecant, secant, and cotangent. We will measure all these relative to a given angle. Notice that there is a theta and a phi here, but I'm currently only listing all these relative to theta. We will deal with both though in a minute, all right? So here's all of it, and some other kind of small things. This is sort of like the long form English word is cosine. It is mathematically notated just as cos. Tangent, tan. Cosecant is CSC right here. So they're all sort of like these abbreviations as saying these are functions, right? So what we're going to see with these side length ratios right here is we're going to come up with a way relative to theta to describe all of these. Relative to theta, side length A is adjacent to theta. Side length B is opposite of theta. And side length C is just our hypotenuse, right? So notice that what we're doing is we're saying A and B are generally interchangeable, but relative to a certain angle, they sort of have a different relationship. You're either the side length that's touching that angle, or you are the side length that is opposite of that angle right there, right? So these labels are specific to theta. If we were referencing phi, B would become adjacent, and A would become opposite, but C would remain the hypotenuse there. So all of these definitions, these 6 different functions that we want to describe, are just going to be 6 different fractions of each of these 3 quantities over here. Sine is going to be the opposite side length divided by the hypotenuse. In our diagram here, it looks like that's B divided by C. But that will change, the B and the C. The opposite hypotenuse will remain. Cosine, we will define the cosine of theta will be the adjacent over the hypotenuse, which looks like A over C. And the tangent of theta we will define to be the opposite side divided by the adjacent side. That looks to me like B over A in this setting. Notice that I've grouped these up into 3 on top and 3 on the bottom. That's because these 3 on the bottom are just going to be the flipped version of the 3 that are on the top. We're going to come to see that there's definitely a bit of redundancy that's associated with trigonometry. We'll kind of define a little bit more than what we need. Base, perpendicular, and hypotenuse. Okay, that makes sense. Base and perpendicular and hypotenuse. I could see that being I do feel like these words are a bit generic out here. I almost wish there was some better math words for those. So cosecant is going to be sort of like the partner of sine. Cosecant is just going to be the opposite relationship as sine. Instead of being opposite over a hypotenuse, it's going to be the hypotenuse over the opposite, which we can just see is going to be C over B. Secant of theta, secant is always going to be partnered with cosine. It's the reciprocal of cosine. That'll be our hypotenuse over our adjacent, which in this case is C over A. And finally, cotangent is going to be the reciprocal of tangent. Those are like partners also. That's adjacent over opposite. And that's going to be A over B. So you should immediately be saying now to me, Tony, how am I ever going to remember all this? And I'm going to burn it into your brain right now. In general, the learning mnemonic that is associated with these guys is so, ka, toa. If you go like ask the internet, how do you remember what our relationships are for sine, cosine, and tangent? This is sort of like a verbalization that helps us with this. So what this is supposed to say to me is sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. So I want to burn this into your brain right now. Here's what my issue is with SOHCAHTOA. I've taught this class a bunch of times, right? And so in the past, I've taught this class where like there's been like a day where I go around and I give a quiz to everybody, and I'm like taking my lap around the classroom, and people are taking the quiz, and I've walked around the classroom before, and I've seen people, and as people typically do, right? You hand out a quiz, people have been studying right before the quiz, and you write your little notes to yourself at the top of the quiz right before you take it. I've walked around the classroom, and I have walked around and seen people write things like so ka like Toa, or like I've seen like that written at the top of the page, and it's like, damn, like they remembered how to verbalize it, but they spelled Sokotoa wrong, and then they have all their answers wrong on the quiz right there. So how do you remember how to spell this nonsense word right there? All right. So I went after watching this happen one quiz, I was like, all right, certainly the internet has the answer for this. Certainly out there somewhere on the internet, someone has come up with like a slightly smarter way to think about this. And so I go to the source of all true knowledge, right, Wikipedia, and I ask Wikipedia. I say, Wikipedia, what's our mnemonic for remembering Sokotoa here? And now this has been long since removed from the Wikipedia page, which is why it's now my responsibility to pass this on to all of you. And Wikipedia gave me like a sentence that helps you remember this. And you can't forget it once you hear it, right? So here we go. Sokotoa. How are you going to remember Sokotoa? Here's the 9-word sentence that Wikipedia, and again, my defense here is Wikipedia told me this. You ready for this? Some old hippie caught another hippie tripping on acid. That's what Wikipedia told me. I am absolving myself of all responsibility for that. I dare you to try and forget that right there, right? So katoa, don't misspell that guy right there. It's going to help you remember all of your trig relationships right there. I do want to point out one last quick little thing right here. Also, how do we remember which ones are partnered with which other ones? Remembering things like secant, cosecant, is that supposed to be the reciprocal of sine or cosine? A good thing to remember here is that there's only one of the 3 originals that has a co in it. The opposites have the co in the second grouping that are out there, right? So sine, since it doesn't have a co, is partnered with the one that does have a co. Cosine, because it does have a co, is partnered with the one that doesn't have a co. And the tangent and the cotangent, if you can't keep those straight, then you're in trouble anyway. The tangent and the cotangent go together. They're reciprocals of each other right there, right? So just kind of like little ways to remember some of the stuff that's out there. So let's use these relationships to identify these 6 trig functions associated with an angle in a triangle right here. So as our first good example here, let's identify all 6 trig functions associated with both interior angles of a right triangle with a leg of length 5 and a hypotenuse length 13. So first things first, draw my triangle here. All right. I know that I've got a side length, I've got a leg of length 5. I've got a hypotenuse of length 13. I'm going to label this with my theta and my phi, and I know that that's a right angle right there. What I would like to do is I want to come up with 12 total things right here. I want to come up with 6 trig functions associated with theta and 6 trig functions associated with phi right here. Now, one of the things that I'm noticing is that we're missing a side length. So I think that our first step here has to be to identify this missing side length. So I'm going to go ahead and do that first. I'll say our 5 squared plus b squared, the unknown side length, must be equal to 13 squared. This will tell me, what are we doing here? A little bit of subtraction. That's what, 169 minus 25. That'll tell me that b squared is going to be, what, 144. And so therefore b must be 12. And again, certainly your calculator is going to help you out with some of that information right there. But I'll say here b must be 12, our unknown side length. So now we know all 3 side lengths. So let's go on down the line here and find all of our trig functions right here. So sine, cosine, tangent, and then cosecant, secant, and cotangent. Then these are all associated with theta. Then we'll do all 6 of them again associated with phi. Right? So again, it is important that we know what angle these are referencing to, because when we say words like adjacent and opposite, those are particular to that given angle. Right? So theta is our point of reference for all these guys. So as we just defined up here, sine is going to be opposite over hypotenuse. And in fact, I guess what I should just do is just leave SOHCAHTOA visible right there. Sine is opposite over hypotenuse. So relative to the angle theta, opposite is 12, hypotenuse is 13. So sine of theta in this triangle looks like it's 12 over 13. Cosine of theta, cosine is adjacent over hypotenuse. Adjacent to theta is 5, hypotenuse is 13. And it looks like tangent of theta is opposite over adjacent. Opposite of theta is 12, adjacent is 5. So 12 over 5. Now, the other thing that we saw over here is that when we defined these 6 functions, these second grouping of 3 are just the flipped reciprocal of the first grouping of 3. Instead of being like opposite over adjacent, it's adjacent over opposite. So all we have to do to find the other 3 is just flip the first 3. I'm remembering that sine doesn't have a co in front of it, so it is the reciprocal of the one that does have the cosecant right there. So this one will be our 13 over 12. Secant does not have a co, so it partners with the one that does have a co up top. So this will be 13 over 5, the reciprocal of this guy. And cotangent has the co, it partners with tangent without the co, and we're going to get our reciprocal there, 5 over 12. Right? So this is how we can identify all 6 of our trig functions just by looking at the ratio of side lengths. So this is kind of just a definition thing right now. We defined these 6 words to be related to 6 ratios. We built the triangle, we identified the 6 ratios. That's all we got going on here. Now, the thing that's going to change ever so slightly is that when we want to do this for the other interior angle, phi, we now need to be a little bit more careful about what we mean when we say adjacent and opposite out there, right? But our definitions are the same. But those are sort of like relative positions, right? That's like using left and right. Those are not very good for directions because left and right change if you're coming from a different direction, right? Similar with this, opposite and adjacent, they're relative to a position. Now that we're discussing the other angle phi here, I know that sine is opposite over hypotenuse, but it's opposite of phi. Opposite of phi is now 5. The hypotenuse, still 13. That kind of never really changes right here. So it looks like the sine of phi is 5 over 13 because sine is opposite over hypotenuse, and opposite of this upper angle is the side length of 5 right there. All right? Cosine is adjacent over hypotenuse. Adjacent to phi, the leg adjacent to phi is 12. Hypotenuse is 13. Tangent of phi, opposite over adjacent, is 5 over 12. Now, before we go ahead and wrap up the last ones, you should look at these top 6 right here now associated with theta and with phi, and you should notice that there's some pretty close relationships there. We're going to talk about those a little bit more at the end of the video here, but some pretty close relationships right here. Hey, Pratik right there. Yeah, we're working through a college trigonometry book right here. This is associated with week 1 of a college trigonometry class. So I have got my, I know I'm flipped right here, College and Algebra and Trigonometry by Sullivan, a 7th edition book. And we are currently in chapter 6 here. We'll be looking at chapters 6 through 9 of this book this semester here, and I'll be making videos associated with these 2 videos a week here on Twitch if you're interested in that. So this is our kind of my college trigonometry course that we're working through here right now, and just getting introduced to our first trig functions here. So, and just to wrap up this example here, as we did over here, our 3 grouping of functions at the end here that are the reciprocals, we just need to flip them around from the ones that we've already determined here. Cosecant is the reciprocal of sine, so I'm going to get our 13/5. Secant is our reciprocal of cosine, 12/13 becomes 13/12. Cotangent is our reciprocal of tangent, so I'll end up with 12/5 instead of 5/12 right there. So we're able to come up with all 6 trig functions of both interior angles just by knowing that it's a right triangle and knowing 2 of its side lengths right there. So what we've done is we've established what all of our ratios of side lengths are, even though we can't necessarily determine the exact side lengths what they must be for any triangle with that angle theta and with that angle phi right there. So hopefully the question that you're asking right now is, do we really need all 6 trig functions? The answer is kind of no, not really. And I'm going to emphasize to you that some of these are more important than the others here, right? So our reciprocal relationships are things like sine of theta equals 1 over cosecant of theta and vice versa. Cosecant theta equals 1 over sine theta. All right, that's a reciprocal. It's a flipped fraction version right there. Yes, Pratik. This is an official lecture for this here. I'm live streaming them in case any of my students want to watch live, and then I record the videos and throw them up on YouTube as well, so any of these can be watched after the fact as well. Our cosine is associated with secant. These are reciprocals of each other. And tangent. Tangent is 1 over our cotangent here, and cotangent is 1 over tangent. All right. So these are our reciprocal relationships. We can flip any one of these and get to any one of the others. So in one sense, if you ever know one, you guaranteed know two of your trig functions because you just got to flip it. We also have a special quotient relationship right here. And one of the things that I'd like to show here, and I'm going to come back to referencing our opposites and hypotenuses and adjacents and stuff like that here, is to notice, look at sine, cosine, and tangent right here. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent doesn't have any hypotenuse stuff in it, but it does have opposites over adjacent. A nice thing to see here is that sine of theta over cosine of theta. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And if we simplify this complex fraction, it's opposite over hypotenuse times hypotenuse over adjacent. And cancel, cancel, leaves us with opposite over adjacent. Opposite over adjacent, that's exactly tangent. All right? So we can see that there's also a quotient relationship here where if you divide two trig functions, you might be getting a third out there as well. Now, this isn't true for like all of our relationships out here, but this is sort of our most special quotient relationship right here, is that tangent of an angle is the same as the sine of the angle divided by the cosine of the angle. And this will be one that we use pretty heavily here this semester. This will help us rewrite lots of things in terms of just sine and cosine. So here's sort of my like kind of a breakdown of how I think about this. It looks like tangent can be written in terms of sine and cosine. It looks like secant can be written in terms of cosine. It looks like cosecant can be rewritten in terms of sine. So what that says to me is that this really boils down to sine and cosine are the two by far most important out of the 6 right here. The remaining 4 can be made up by manipulating sine and cosine. So one of our big strategies for problem solving this semester, and we get lots of different trig expressions, is to convert everything in terms of sine and cosine so that we can kind of have a little bit more common language to discuss here. Yeah, Pratik, if you have questions about the things that we're discussing right here, I suppose I'd be able to answer the question. On the one hand, I'm sort of trying to make a good video for later, but if they're relevant questions, if I make a mistake, anything like that, I'd be happy to interact with you here. So if I ignore you, that might be because I'm trying to like keep some consistency for a good video. But again, if you've got questions relevant to the topic, then I'm sure that my students do as well. So you're welcome to flop them out there and chat. So, based on these relationships that we're looking at right here, one of my questions might be, if I know a trig function of any given angle theta, can we find the others, right? If I knew, for example, that sine of theta is 1/2, could I determine what cosine of theta is going to be? To do this, one of the ways that we can do this, we're going to come up with 2 different techniques for this, is that we can convert what we know about the Pythagorean theorem into information about what we will call the Pythagorean identity. And I just emphasize the because there's actually going to be 3 Pythagorean identities, but let's not get ahead of ourselves here. What I want to do is convert this Pythagorean theorem information into information about angles rather than information about side lengths here. So what I'm going to do is I'm going to label a general triangle here. Right? So I've got a theta. Relative to theta, this is the side that I would call adjacent. This is the side that I would call opposite. This is always going to be labeled as the hypotenuse right there. Right? What we know from the Pythagorean theorem is that it looks like this is sort of like a squared. This is going to be like our b squared. This is going to be like our c squared. So the Pythagorean theorem says Adjacent squared plus opposite squared equals hypotenuse squared. So what I'm going to do is I'm going to do a little bit of algebra with this expression right here. Now what I'm going to do is I'm going to just divide everything by hypotenuse here. Or excuse me, by hypotenuse squared. All right. So what we can see we've got now is I can rewrite this guy now as, it looks like this is a number squared divided by a number squared. So algebraically, it's acceptable for me to sort of factor out that squaring right there. So I'm going to rewrite this as adjacent over hypotenuse squared plus opposite over hypotenuse squared equals, and these are the same. This is hypotenuse squared divided by hypotenuse squared. That's just 1 right there, right? Now to complete what I want to do for the Pythagorean identity, we just got to remember that these are ratios of side lengths now. These are our trig functions. What are they? From our SOHCAHTOA, I can tell this is going to look like cosine. Cosine is adjacent over hypotenuse. Sine is opposite over hypotenuse. So it looks like I'm getting here cosine squared of theta plus sine squared of theta equals 1 right here. And this is what we refer to as the Pythagorean identity, not to be confused with the Pythagorean theorem. So the Pythagorean theorem is just side lengths. Pythagorean identity relates trig functions of angles, but with the same exact idea, right? We just literally wrote the Pythagorean theorem in terms of adjacents, opposites, hypotenuses. We did one division, and then we just rewrote things based on their trig definitions right there. So notice that this now means that the answer to this question up here is yes. If you knew what sine of theta was, then we could solve for what cosine of theta should be. Hey, yeah, Pratik, cool. So I'm also doing Calculus 2 and differential equations this semester as well. So maybe trigonometry is not what you're looking for, but maybe some differential equations or something like that might be a little bit more up your alley for some other videos that I make out here. So if you check out my schedule, you can see some of that stuff, and feel free to pop in if you will. So as I said a second ago, there's really actually going to be 3 of these guys. We can do a little bit different of a division up here, and it'll give us a little bit different series of ratios up here rather than dividing by the hypotenuse squared. So we've got some options. We'll come back to that guy in a second. For right now, I want to use this. Let's do an example that's associated with these guys that are right here. So let's do exactly what we suggested right here. Given that sine of theta is 1/2, let's find all 6 trig functions, but let's try and do this kind of like in a different way. Let's kind of think a little bit differently right here, right? So what I want to say here is specifically, I want to do this by using the Pythagorean identity. We'll use a different strategy for this in the next example that you can see coming up down there, right? So what I know from the Pythagorean identity is that sine squared theta plus cosine squared theta is 1/2. Right? I know the value of sine, right? So it looks like I'm going to be getting 1/2 squared plus cosine squared of theta equals 1/2. Right? It seems to me like I can solve this now, right? 1/2 times 1/2 is 1/4. And I can now go ahead and subtract 1/4 from both sides. We're at it 1/4. And I can now go ahead and take my square root of, wait a minute, what am I? Oh my, okay. I was like, oh, I'm getting the wrong answer here. Okay, let's stop and identify my mistake right here. I just copied down our Pythagorean identity statement wrong right here. This is that cosine squared plus sine squared equals 1. I, for some reason, wrote, well, I know why. I wrote 1/2 just because I was thinking about that guy right there. Let me go ahead and fix this real quick here. Cool. Okay, that was a 1. That's a 1. That's a 1. Now I'm going to subtract over my 1/4. If I take a quarter away from 1, I'm left with 3/4. And now I can go ahead and take my square root of cosine. And again, it's going to be the case that at least for right now, we're not worried about our positives and negatives right now. If you're taking algebra classes, you should know that we should be getting plus or minus the square root of 3/4. But we're interested in positive lengths for right now. We'll get some longer, or we'll get some alternate cases with positives and negatives coming up here in the next couple weeks, but not yet. And finally, I just want to do a little bit of simplification here. I can't simplify the square root of 3, but I can simplify the square root of 4. So this is much more commonly looked at as square root of 3 over 2. So here's where we're at so far. So far, we know that sine of theta is a half. We know now we've used the Pythagorean identity to find that this is root 3 over 2. So what could we find next? I want to know all 6 of the trig functions. I want to do the least work possible to find all 6 trig functions. That's also important. I'm lazy. That's critical to this. So the next thing that I'm thinking is if I know sine and cosine, what's the next thing I can find? I know that sine and cosine can combine to give me tangent. That's one of the other relationships that we just identified there. So sine divided by cosine should be giving me my tangent. So let's see what we get when we do this now. Tangent of theta is going to be sine theta over cosine of theta, which is going to give me 1/2 over root 3 over 2. And if I go ahead and simplify my complex fraction here, that's 1 over 2 times 2 over root 3. You should notice that these 2's are going to cancel, leaving me with 1 over the square root of 3 right there. All right. So now I've got my value of tangent, and again, I'm lazy. So what am I going to do to find the rest? Well, I know that the remaining 3 trig functions are reciprocals of the first 3 trig functions, right? So sine does not have a co, so its reciprocal is the cosecant, and it is just the reciprocal. So that's 2 over 1, or just 2. Similarly, cosine has a co in it. Its partner, therefore, is secant without the co in it, and it will be the reciprocal of that value, 2 over root 3. And finally, our last one, cotangent of theta, reciprocal of tangent, so that should be root 3 over 1, or simply just root 3. So these are bireciprocals. All right. So this was good. We used the Pythagorean theorem, and in fact, we're in a sense talking about like triangle relationships here, and we didn't even need the triangle to do this, right? We used the Pythagorean theorem to get us from sine to cosine, and once we had just sine and cosine, just 2 of the 6, that got us all 6 of the functions that we were looking for. Tangent is sine over cosine. The remaining 3 are just reciprocals of the first 3 that we got out there, right? So let's do a problem that looks a lot like this, but what I'm going to specifically do in this next problem is I'm not going to use the Pythagorean identity at all. I'm going to show you a different way that we can come up with these same types of values that are right here, right? So this problem, I just want to show you, this problem is very, very, very similar. I'm giving you one of our trig functions values, and I want to know all 6 of the trig functions values associated with that same angle there, right? So it's kind of the same problem, but I'm going to approach it with a different approach right here, all right? So the difference is I'm going to do this by drawing the relevant triangle. So I want to show you what I mean by that. When I say that cosine of theta is root 2 over 2, we defined cosine as a function to be describing to us the adjacent side divided by the hypotenuse of a right triangle. So what I'm going to do is I'm going to help myself draw the triangle using that information. I'm going to draw any old right triangle. I'm going to label, super importantly, you have to label where theta is because adjacent is relative to where theta is. So that matters in there, right? So, and it doesn't matter. I could pick either one for theta. I'm going to end up with all the correct relationships. You just got to pick something, label it, right? So cosine of theta should be adjacent over hypotenuse. So it seems like the adjacent to theta should be square root of 2. Our hypotenuse should just be 2. I want to go ahead and find out what my missing side leg is over here, right? So root 2 squared plus b squared equals 2 squared. So 2 plus b squared equals 4. I'm going to subtract 2 over to the other side over here. B squared equals 2. And that's going to tell me that b is also the square root of 2. Right? So it doesn't look like I actually drew my triangle proportionately correctly, but that doesn't matter out there. I don't care about how your triangles look. I care if they're labeled properly right there. So I now have a triangle that I can use to help me reference all of my side lengths now. So notice that by just building the triangle, I can build a triangle that has this being true. Cosine of theta is root 2 over 2. I can now grab all 6 of my ratios from this one triangle right here. So I'm going to just go down the list here. Sine of theta. Sine, so katoa. I should even just keep on writing it right here. So Krakatoa. Right? So sine is opposite over hypotenuse, so that's root 2 over 2. Cosine, that was given to us, but we can verify it, which we should. Adjacent over hypotenuse is root 2 over 2. That matches. Tangent, I could think of, one way I could think of it is as sine over cosine. And notice that since these are equal, I should be getting 1. Another way I can think about tangent is it is opposite over adjacent, and that's root 2 over root 2, which is 1 in this case right here. So there's my first 3. Now I can go ahead and get my remaining 3 trig functions right here. If sine is opposite over hypotenuse, then cosine should be hypotenuse over opposite. Or since we've already written these, I can just go ahead and do our reciprocal, right? Hypotenuse over opposite. Got it. Secant, adjacent over hypotenuse. Or sorry, hypotenuse over adjacent right there. Said it backwards. And finally, our tangent here, or sorry, our cotangent here, you should notice, we're taking the reciprocal of 1. Well, it's still just root 2 over 2. I mean, it's a flipped version of root 2 over 2, but that doesn't change anything. We're landing here still back at 1 there, right? So notice that this was an entirely different approach to essentially an identical problem. So the cool thing is here, if you're given one trig angle, you really do have several different ways that you could go about this. We could either use the Pythagorean identity to identify immediately other trig functions associated with that angle, or we could draw a triangle that has this property, that cosine of theta is root 2 over 2, and then we could use that built triangle to identify all 6 of our ratios right there, right? 2 totally different strategies for essentially the exact same problem. You are welcome to choose either strategy. I will say that later this semester, there's going to be some slight pros and cons to choosing one of these over the other, but when that comes up later, we'll discuss that right there. So, I said to you earlier, there are a couple alternate forms of the Pythagorean identity, and in fact, there is more than one Pythagorean identity that is available to us. And so let's kind of look at those guys real quick here. We started with the Pythagorean identity, which I'm just going to make a list over here. I'll just call it the first one. This was sine squared of theta plus cosine squared of theta equals 1. And all I'm going to do is I'm going to just do a little bit of light algebra to this guy, and we're going to see some other nice things, easy things pop out right here, right? So one thing I'm going to do with this guy is I'm going to take the expression sine squared theta plus cosine squared theta equals 1, and I'm going to divide everything by sine squared of theta. You should notice that sine squared of theta divided by sine squared of theta, those are the same number, so that's 1. Cosine divided by sine, well, I saw earlier that sine over cosine is tangent. Therefore, cosine over sine must be cotangent. And those terms are squared. And finally, we know that the reciprocal of sine is cosecant. So this looks to me to be cosecant squared here. So it looks like we've got here our next one here, which is, and typically this is written like ever so slightly differently. I'm just going to rearrange the order. Cotangent squared theta plus 1 equals cosecant squared of theta. And our third one, we're going to do almost the exact same thing right here. I'm again going to start with our original Pythagorean identity. And this time I'll divide everything by cosine. In this case, sine over cosine is tangent, and it's squared. Cosine over cosine squared is 1. The reciprocal of cosine is what we've called secant, and it's squared. So there we go. So here's kind of our big takeaway from this. If you ever know any one trig function, you can always directly relate that to one other trig function using a Pythagorean identity. The one hang up here is that it's always going to be a squared relationship, and that's going to hurt us a little bit later. We're going to want to come up with some relationships between trig functions that don't require quantities to be squared, but I'm getting ahead of myself. That's a month from now that we're going to talk about that. So let's take away the positives from this, which is knowing any one trig function. Notice that all 6 of our trig functions are represented once here. If you know any one trig function, you can always use one of the 3 equivalent Pythagorean identities to solve for one of the other trig functions that's out there. It's always one of the things that we can do here. But again, notice that our slight inconvenience here is the forcedness of these all being squared quantities here. But we'll come up with alternate routes to do things like this when that gets to be an issue for us, which it currently is not. And I will also say to you, again, in a sense, these are 3 equivalent identities, but it's certainly the case that sine squared plus cosine squared equals 1 is by far going to be the one that we use the most this semester. So this is the one where like this should be burned into your brain. Every once in a while, I've got to go like look up which ordering these go and like which ones partner together, or just like rebuild it like I do right here. I kind of forget these sometimes because I use these a lot less, but this number 1 right here is number 1 for a reason. So let's simplify some expressions. Let's just see some things that should be true based on these 3 Pythagorean identities here. So I've got 3 different expressions that I want us to just simplify, right? So the first one here, tangent of 30 minus sine of 30 over cosine of 30. One, when we see numbers like 30 where there's not pi involved, I don't necessarily intend to write degree symbols on literally every single thing, which would probably be appropriate, but it's pretty typical that if we see a number like 30, that's an indication that we're thinking degrees, not radians here. What we want to remember is that we have seen the identity earlier today that sine of theta divided by cosine of theta equals tangent of theta. So my rewritten version of this guy would just be to say tangent of 30 minus this is the tangent of 30 right here. That's one of our definitions of tangent, sine over cosine. And so it looks like here we're just getting tangent of 30 minus tangent of 30, which is clearly going to be 0 right there for that quantity. In a kind of similar sense right here, we want to, again, do some simplification, rewrite things the way that we know that we can. Whenever I see secant right away, I'm like, dang, I don't want to deal with secant pretty much ever, so let's not. So I'm thinking to myself, I know that secant is the reciprocal of cosine. And since it's 1 over secant, I can just rewrite this as just cosine, and we'll retain the fact that it's squared. So it looks like this is the same thing as sine squared of 10 plus cosine squared of 10. And now this seems to me, now it looks like we're dealing with squared trig functions. It seems to me like we should be experiencing some sort of Pythagorean identity relationship. The Pythagorean identity tells me that I don't care what the angle is. For literally any angle theta, these relationships are always going to be guaranteed to be true. These are called identities because they're always true for any value of the variable, not just for some special value. So the fact that this is 10 degrees doesn't matter at all. The thing that does matter is that these are both 10 degrees. If you ask me what's the sine squared of 10 plus the cosine squared of 20 degrees, I have no idea. Actually, I can do that one, but it would take me like a lot of work and like a bunch of content from chapter 7. Since these match up, this says to me, I literally just get to call this 1 by the Pythagorean identity. Sine squared of any angle plus cosine squared of that same angle is guaranteed to always reduce down to just 1, right? So sometimes, hopefully the lesson that you're taking away right away is, sometimes we're going to see some pretty gross looking trig expressions that turn out to actually be representing very simple quantities right here. So trust that that's going to happen a lot. Our final one here looks gross just like the first ones did, and let's see if we can kind of work through this. This is sine of theta times the sum, sine plus cosine. We're adding on to that cosine times the difference of cosine minus sine. So I'm thinking I might want to like get some terms grouped up here. So a typical strategy that I have is multiply everything out, group my terms up that I think go together, and recombine everything back together. So my first step here is going to be to do some distribution here, right? I'm going to distribute the sine and the cosine across their multiplication groups. So I'm going to get here sine times sine is sine squared plus sine theta times cosine theta. I don't have any better way to write that. Sine theta times cosine theta. Plus, again, I'm going to distribute here. I'm seeing a cosine squared theta, and then when I multiply cosine out here, cosine times negative sine is going to give me minus sine theta cosine theta. Well, this looked like that just worked out really kind of nice for us here. The two things that I'm seeing are, one, it looks like that guy and that guy are going to cancel with each other. There's a positive and a negative of it. And then the terms that I have remaining are just sine squared theta plus cosine squared theta. That's 1. It's the whole expression is guaranteed to be equal to 1. And notice the even crazier thing about this. At least in the first two examples, I specifically plugged in like a number, like how many degrees or radians it was. This literal entire expression, no matter what angle ever you use for theta, will always be equal to 1. And we know that's true just by a little cancellation and a little application of the Pythagorean identity right here. So this is a little bit of a primer. Once we hit chapter 7, we're currently in chapter 6. Once we hit chapter 7, we're going to deal a lot with some complicated trig expressions here. And what we're going to see is that we're going to want to be able to do this like algebraic manipulation, use the identities that we have to rewrite things much, much more simply. These are some early versions of that right here. All right. So let's hit ourselves with a few examples here. We really just have sort of like one essential big idea left, and I just want to do some more examples that are going to look like some of the things that you guys should expect to see in your MyOpen Math homework out here. So let's take a gander at some of these guys right here. I think, what do we got? 3 examples, and then sort of our last thought right here. So let's work through these guys. Our first last example. A 10-foot ladder leans against the wall. This is like one of the most cliche examples that early in a trig class that you're ever going to see right here. We got to hit it because it's a cliche, but this is really, really important. This is like a very typical use of basic use of some trig functions right here. A 10-foot ladder leans against the wall. The angle between the ground and the ladder is 65 degrees. How high up the wall does the ladder reach? So what I'm picturing for myself is I have a wall, I have the ground, and I have a ladder leaning against the wall in such a way that there is a 65-degree angle between the ladder and the ground, right? Is that what I said? Ground and ladder, 65 degrees, right? This is my right angle, as is the case in... Okay. My garage apparently is slanted like this, I've been learning lately, but walls are supposed to be perpendicular to each other, just not when you live in a swamp like we do. This is what I know. The other thing I know is that the length of this ladder is 10 feet tall. What I want to know is how high up the wall does the ladder reach? So I'm going to label 2 things here, but we want to know only one of them. Since I noticed that I kind of drew this as if it's like on a coordinate axis rather than like me literally drawing like a corner in a wall, I'm going to label this side length as x as an unknown distance from the wall. And I'm going to label this leg right here as y, the height up the wall to the top of the ladder. What we want to know here is y, but realize that I could have just as easily asked you a question such as, how far from the wall is the base of the ladder? In that case, you'd be interested in solving for x right here. So here's what I'm thinking. We want to know y, right? That's the height up the wall. What it seems like y is, let's say here, relative to the angle, 65 degrees, y is opposite, and the known side length of 10 is the hypotenuse. So my question to you is, based on this information, what trig function do you think that we should use to help us figure this out? I see that we're talking about opposite and hypotenuse. I know that sine of theta is the opposite divided by the hypotenuse. So that says to me, let's build a sine expression so that we can discuss what the value of y must end up being. So this says to me, I can build the expression sine of what angle? Well, the angle that I want to compute the sine of here is 65, because that will allow me to talk about both y and the number 10. So sine of 65 in this case right here, sine should be opposite over hypotenuse. That's going to give me y over 10. Our goal was to solve for y. All I therefore have to do is multiply both sides by 10, and I've got it here. So one very important thing that we need to do right now is this. I want to scroll back up and shake my fist at you once, and then scroll back down and unshake my fist. So here's the deal. Way back up here, when we were doing our first solving of our side lengths of our triangles right here, I said to you, I very much want you to leave things like square root of 29 is square root of 29. Don't give me a decimal for that guy. I'm not going to recognize 317, whatever it's going to be out there, I know what square root of 29 is. It's exactly correct, and I can perhaps identify where it came from. Don't give me things like that as a decimal. That's not helpful. On the other hand, if I'm sitting in my garage and I say to you, hey man, how high up the wall is the ladder touching the wall? And you said to me, oh, square root of 67. I would be upset with you if you said that because I'm asking for a number of feet. In our real world applications, this is absolutely where we now want to be in decimal land. So if you were to say to me, oh, it's 10 times sine of 65 degrees feet up the wall, that's a very bad answer for a real world application. So this is where we want to go to our calculator to do this. The big message that I want to point out to you is if you are using a TI calculator, and I know my screen's flipped, but I'm going to show this real quick right here. On your calculator, there is a button up top that says mode. It's sitting right there next to my blue button. It says mode right there, and I'm going to press mode. And when we get mode, your screen might look a little bit different than this, but it is definitely going to be the case that you have an option that says radians or degrees. Right now, radians is what is in bold. And again, I know that this is flipped, but I'm also assuming you guys can probably read my flipped writing right here. I don't want to be in radian mode because I'm about to ask it for the sine of 65 degrees. So it matters that I go over to degree and hit the enter button down here, and it will move that black highlighting over to degree mode. I am telling all of you right now that every person in this class is going to get some answers wrong this semester because you're going to be in the wrong mode in your calculator. It's a mistake that everybody's going to make. Don't feel bad when you do it, but always, every time you compute a trigonometric function in your calculator, stop and say, wait, am I in radian mode or am I in degree mode? Tons of people are going to make a little mistake like that this semester. So just be aware in the mode in your calculator. Here I want to be in degree mode because this is a sine of 65 degrees. So I'm going to do 10 times the sine of 65 in my calculator. So it's just typed as 10 sine 65, and I can go ahead and hit enter, and it's telling me 9.063. So it seems like that is the number of feet up the wall that the ladder is making contact with the wall, given that it is leaning at a 65-degree angle relative to the ground right there. All right? So I think the big lesson also associated with this one, aside from just be careful with your calculator, is think about what trig function is of interest to you. In this problem, we only knew the one angle of 65 degrees, and relative to that angle, we knew one side length, 10, the hypotenuse, and we wanted to know another, the opposite. Since opposite and hypotenuse were the two things that I knew and wanted to know, that said to me, sine is the most appropriate trig function for me to use in this context because opposite and hypotenuse are involved. That's why I built a sine trig function as opposed to any of the other ones that were out there. Right? So that's our first example. That was a little bit of our easier one. Let's do our hard example for the day right now. It'll be our second to last example, and we'll be close to the end here. Find the length x. And the very important part about this is we clearly have like a little bit more than just a triangle right here. So I want to kind of suggest to you that there are several triangles that I see here. I see 3 triangles here, and I want it to be real clear to you that I see 3 and that you should be seeing 3 as well. The first triangle that I see is this small right triangle right here. The second triangle that I see is this small oblique triangle out here. This is not a right triangle, so it's going to be hard for me to talk about this guy. The third triangle that I see is the full, complete right triangle on the outside. So I'm thinking of this as 2 sub-triangles, sort of, mashed together to make one overall larger triangle that's out there. There's really 3 triangles in this picture. That's important. So what I want to know is x, but you should be immediately concerned because x is a side length of a non-right triangle, and we're like literally like a month away from discussing non-right triangles. So it doesn't seem like we're going to be solving for it directly. So what I'm going to need to do is get more information about this triangle here so I can help myself find it. I won't be able to solve for x directly because x is the side length of a non-right triangle, but it is part of a leg of a right triangle. And I think that's going to help us out right here. So here's what I'm thinking. I'm going to label a few additional values that are on this thing right here. Kind of what I'm picturing to myself is this seems to me to be a quantity that we could go ahead and identify. Since it's a leg of a right triangle, I'm going to call it B, like I often call my unknown leg of a right triangle. You should also notice that here's another unknown right triangle length right here. And just for lack of anything better to call this, I'm just going to call it y, just to call it something. I just need a letter right there, right? Normally I would have called it b, but I've already got a b that's sitting right there, so whatever. So the point is, it seems to me like if we can find this side length right here of b, and if we can find this overall side length here of y, then I could subtract the length b from the length y, and that would leave me with the length x. That's the important relationship that I'm building right here. So it looks to me like b plus x equals y. We want to ultimately end up solving for x, and so it looks like we can get that by doing this. So as I've set this up, my goal is going to be to find b, find y, subtract the two, and I think we'll be able to identify that remaining length that's right there. Remember that right triangles are your friend, not oblique triangles currently, so it's important that we collect information from right triangles. Right? So the first triangle of interest, the one with the b that is involved here, so I'm going to kind of call this my step one, is I'm just going to extract that one triangle from the drawing right here. This is really helpful because I know that one of the things that gets tough for people is there's a lot of information going on at once. Narrow your focus, right? Put your horse blinders on. Only look at the part of the problem that's currently relevant to you. If I'm interested in knowing about B, none of that X or that 20 degrees has anything to do with it, right? So I'm isolating the things of interest. In this case right here, it looks like I know the angle of 60. I know that 10 is opposite and B is adjacent, right? So relative to 60 degrees, 10 is opposite and B is adjacent. Based on this, we should use a tangent expression to help us relate these guys to each other. Opposite over adjacent is tangent right here. So I'm thinking to myself, I can make the statement tangent of 60 degrees should be equal to opposite of 60 is 10, adjacent of 60 is B. I'm going to multiply both sides by B, and I'm going to divide both sides now by tangent of 60. And it looks like I have an expression for B. We could get a decimal for this. I'm going to wait and just go to the calculator one big time at the end right there. So I'm going to leave that as my length for B. But notice that means that we found one of the key pieces to this puzzle right here. Right? Now as my step two, we can play the same game, but let's look at our big triangle now. Now I want to find Y, because if I know Y and B, I've got X. Right? So now let's go ahead and look at our big triangle here. In our big triangle, I've got an angle of 20 out there in the corner. My unknown side length is y. I still know that that leg has length 10. You should notice that this scenario right here is very similar to this scenario. In fact, the only thing that changed is 60 became 20, and we're calling our variable y instead of b. This is still a tangent type scenario because the relative to the one angle I know, opposites and adjacent are the two legs that we are currently discussing right here. Right? So I think that I can do a very, very similar thing and say tangent of 20. Tangent of 20, opposite over adjacent, is 10 over y. Again, I'm going to multiply both sides by y. I'm going to divide both sides by tangent of 20. I now know an expression for b. I now know an expression for y. I now know that I can just subtract these guys and identify the overall value of x. 10 over tan 20 minus 10 over tan 60. And I'm now just going to go to my calculator one single time so I don't have to do a whole bunch of rounding out there. 10 divided by tangent of 20, I'm still in degree mode, that's important, minus 10 divided by tangent of 60. In this case, I'm getting 21.70. By the way, I'm rounding to two decimal places right there in my calculator. I got 21.701. Notice that when I do include the zero on the end out there, although it technically didn't give us like more information, well, it did give us more information. It says even if you were to go an additional decimal place further, there wasn't like more amount out there. So that 0 right there is valuable, even though it technically didn't change the quantity of the number right there. It says I did get 2 decimal places of precision. There just wasn't anything to put in the hundredths place right there based on the rounding that we did, right? So this looks to me to be our value of x here. Right? So remember, we deal with right triangles. In this scenario, the side length was associated not with a right triangle, so we had to a little bit more indirectly come up with the information. I kind of knew where I was going with this problem and immediately labeled my b and my y. That might not necessarily be the case for you, but you should start to get comfortable with the idea of, I don't know, just solve for some stuff. Find values that might be relevant to you. It might be the case that you maybe solved for a length that you didn't necessarily need. That's not the end of the world out there. If you would have found either of these hypotenuse lengths, those weren't going to be directly relevant, but like that's okay. It's not the end of the world if you do a smidge more work than was technically required. Hopefully you can get over that right there, right? It's like identify some features of the triangle out there, and we can think in terms of identify variables for yourself, name things, label things well. That will help you stay organized for these problems that are a little bit more involved here, right? So, last major example here, and then we'll just sort of give a last thought that's down there. This one says, solve the given triangle. Remember that to solve a triangle means to find all 3 side lengths and all 3 angles. Right? And the interesting thing here is that we only have, we have 2 angles and we have 1 side length right there. So it's not clear to me how I'm going to get more side lengths, right? I can't just directly go to the Pythagorean theorem here. The Pythagorean theorem is going to require that we know 2 side lengths so that we can get the third, and I don't have that going on, right? So I can't go for side lengths right away. So my question to you is, what is the missing angle? Now, this is the reason that we're doing this problem right now is that we can state a basic fact of all triangles. All triangles have that the sum of the 3 interior angles is always 180 degrees or pi radians. Right? Always. Every single triangle that's ever been drawn in the history of triangles has 180 degrees as the total number of degrees associated with that triangle there. Right? So what we've kind of got right here is we've got this missing angle. Well, I know 2 of my 3 angles, right? So it should be the fact that we have that 180 is the total sum. That should be the 90 degree angle plus the 55 degree angle plus, I'll call it theta, the unknown angle that's sitting out there. You should also notice that in every right triangle, one of the angles is 90. Therefore, out of the total 180 degrees, there's always just going to be 90 degrees remaining left between the other 2. And so it looks to me like in this case, we're going to get a 35 degree angle is what should be associated with this triangle right here. So I'm going to draw my, as we complete the triangle right here, I'll draw my new one. This is 55. This is 10. That's our right angle. So the first thing that I did is I determined that's got to be 35 degrees because the whole thing has to be 180. In every right triangle, 90 of the 180 is already accounted for, leaving only 90 remaining. And so these 2 angles are always, always, always going to add up to 90 degrees right there. All right. So I now know all 3 angles. To be finished solving the triangle, I need to know all 3 side lengths. But again, I can't go directly to the Pythagorean theorem because I need to know 2 of the side lengths to get the third, and I only know 1 side length. So it looks like I'm going to have to do some sort of trig to help myself get there rather than just a little bit of algebra, right? The good news for us, though, is that, and maybe I'll just label these as A and B right here. That's not going to be enough room because I know we're going to get some decimal values right here. I'll just call it A and B like this, and we'll get, I do have room for B. And we'll go ahead and identify what kind of decimal approximations we're going to get for these guys right here, right? So if I was interested in finding A, I know a hypotenuse length, and I really have then therefore some choices, right? I could use sine, I could use cosine, because I know several different angles right there, right? So I'm just going to say lots of choices of trig function. Solve for A and B. And in fact, there's so many ways that we could do this problem that I really just couldn't possibly do all of them, but I am going to talk through some other options that we have out here of some choices that I'm making along the way. One thing I could do, who cares? I'll pick a 55. Let's see. Do we want to do sine or cosine? I'm not even going to. Okay, let's say I want to solve for A. Let's say I want to solve for A first. If I want to solve for A, which is a choice, I could solve for B first. And if I wanted to use the angle 55, and I could use the angle 35 first, also, it's just a choice that I'm making, then what trig function should I use to relate 55 and A? Since the only other side length known is 10, relative to the angle 55, A is opposite, and 10 is the hypotenuse. Opposite and hypotenuse go with sine for so katoa there, right? So I could make the statement sine of 55 degrees is opposite A over the hypotenuse 10. To solve for A, just multiply 10 on both sides. That was easy. Now, notice that I now know what A is. I have my exact form of A right here. I'm probably going to want to get a decimal for this one right here. I don't like giving side lengths in terms of trig functions. I do like giving side lengths in terms of like square roots, but we don't have any of those in here. So I'll probably go to my calculator for this. Notice now that we have actually an option. Since I now know the hypotenuse and one of the leg lengths, I could now use the Pythagorean theorem to get the other side length over here instead of using another trig function. But I kind of think we should just do another trig function here since that's a little bit more the lesson that we're discussing in this context right here. So let's now make an expression for B. All right. Now, again, I have choices. I could use the 35-degree angle. I could use the 55-degree angle. I could, but what I know is I would probably like to use my clean number of 10. Technically, I could use A in this context. 10's a cleaner number, so I'm going to use that guy. And so I'm thinking to myself, I don't know. And again, let's pick 35 just for the sake of doing something different. There's so many options. You can't pick wrong in this guy, basically. Let's use our 35-degree angle. Relative to the 35-degree angle, notice that B is opposite, just like A was opposite 55. B is opposite 35 here. So I could talk about the sine of 35 being B over 10. And again, real quick, I just got to do a quick multiplication by 10, and I'm done here. It looks like B is going to be 10 sine 35. There we go. We've solved for A and B and all of the side lengths that are out there, or all the angles that are out there, right? So I can now go hit my calculator with this. Again, we're in degrees, sticking it out in degree mode. I know I yelled at you guys all about your radians last time, and now here we are all in degrees. Don't think that we won't be using radians. We'll be doing plenty of radian stuff here this semester. What I'm seeing in my calculator for my decimal approximations here, and yours should be matching this to, I'll go 3 decimal places here. I'm seeing for A, 8.192 if I'm rounding to 3 decimal places. For B, I'm getting 5.736. And you should be able to, by the way, verify that this number squared as a decimal plus this number squared as a decimal is going to give you 100, which is 10 squared right there. The Pythagorean theorem's got a hold. So that's a good way for you to check your answer with this, is come at the answer from a different route and see if things are verified. So I would say now that we have solved this triangle because we know all 3 angles and we know all 3 side lengths right here. All right, so solving a triangle is valuable. One of our big parts of the very end of chapter 7 and then of chapter 8 is going to be solving non-right triangles, and that'll take a little bit more work, but we're going to be very prepared for it by the time we actually get there. Right there. Right? So let's talk one last little thing right here. Let's get some definitions and then see how those definitions relate to our trig functions, and we'll call it a day. We say that two angles are complementary if they add up to 90 degrees. So in every right triangle, it is the case that the two angles right here are always complements of one another. Complementary. They will always add to 90, so that when we add the additional 90 down here, we always get that 180 degrees. Slightly less importantly, we refer to two angles that sum to 180 as being supplementary. You should notice that that will never apply to a triangle, because if two angles in a triangle added up to 180, then there is 0 degrees remaining for the third angle, meaning that that is a triangle that is so low that it's actually just like a flat line. It's like collapsed down onto itself right there. So in fact, no longer a triangle right there. So complementary and supplementary just sort of go hand in hand. Add to 90, add to 180, but complementary is much, much more valuable to us because that's talking about triangle stuff right there. The two interior angles that aren't the right angle are always complementary. So as our sort of last thought, trig functions of complementary angles, I want to kind of come back to this guy that we did right here. I sort of suggested to you when we did this example that there are some pretty special relationships that we were seeing right here. And I want to remind you that theta and phi are complements of one another. So can I do this? Will you be nice to me, Microsoft Word? Let's see if Microsoft Word likes me today. Oh, me and Microsoft Word, we're tight today. This is good. This is good. So I will say copied from above. All right. So what I want to do is kind of really talk about these relationships that we're seeing in here, right? The very big thing for us to notice here, and I'm going to switch colors of my pen just so that I can kind of keep this stuff distinguished here. So, by the way, I was using some purple earlier. I'm going to use some green now. If anybody in here has any, like if, I'm going to generally use like purple, green, and orange here for some colors. I'll try and avoid doing things like green and red because I know that can be a colorblind issue. If you don't like any of the colors that I'm using, you can totally just say, hey, Tony, can you not use that purple anymore or something like that? And I can easily pick out whatever colors are more convenient for you. So if you have any color preferences, just hit me up. I can always change to meet that need there, right? So theta and phi are complementary always, right? In this diagram right here, they are the two additional angles that we're looking at. This says to me that theta plus phi equals 90 degrees. And the real important thing that I'm going to do here is I'm going to do a little subtraction. Theta, therefore, is the same thing as 90 minus phi. And we saw this in our previous example, right? 90 minus 35 is 55, and conversely, 90 minus 55 is 35. You could do it either way. 90 minus one of them gives you the other one. That's always going to be the case. The next thing that I'd like to kind of point out here is it seems like these were giving us the same answers. What's up with that? And I could draw a similar one for the tangents and the cotangents. I won't, just for the sake of clarity of what I'm actually trying to draw right here. But the point is, it seems like there's some other close relationships associated with these complements here. I'm noticing here that the cosine of theta seems to be equal to the sine of phi, whatever the other angle is inside the triangle, and vice versa. And even that the cotangent of theta equals the tangent of phi, and all that good stuff right there. And so I'm seeing here, if this relationship is going to hold in general, it looks like from above, we see sine of theta equals cosine of phi, which is really telling me that sine of theta equals cosine of 90 minus theta, right? That's what I'm getting from this relationship right here, right? And we could go on down the list here, right? Cosine of theta is the sine of phi, which tells me cosine of theta is the sine of 90 minus theta. Tangent of theta equals the cotangent of phi, which tells me tan theta equals cotangent 90 minus theta, right? So let me see if I can get rid of that little errant dash right there. Oh, no, took the whole thing. All right. So there are 3 more of these, right? That go the other 3 relationships, 6 total in the total right there. But this is really good because that means to me that if I were to tell you something like, so if I told you that cosine of 20 equals, I don't know, x or something like that, then what that means is that we also know that what? Cosine of 20? Cosine of 20 should be the same thing as sine of 90 minus 20. So that would be sine of 70 must also then be equal to x right there as well, right? We can use these complementary relationships right here to take in information about one trig function to get information about a different trig function right there. So what your kind of takeaway from today should be is there's sort of a ton of things that we define today, but with all these sines and cosines of theta and of phi and trig, or of cotangents and secants and cosecants, there are a ton of underlying relationships between all of these functions here. And so what our mission really is over the course of this chapter 6 is to say, we want to really get used to all of the ways in which all of these things are heavily interconnected. Seeing what things are the same as each other, are closely related to each other, seeing if I knew one object, that means I can solve for the other object, saying if I knew this piece of information, I could draw the triangle that's associated with that. There's a ton of interconnectedness here, and that's really sort of the theme of this section. This section is really about defining these things, but the goal of this chapter overall is to see the interrelationship between lots of these pieces of information that we've identified here today. So really kind of your goal here is really to get used to just the idea of using sine, cosine, tangent, cosecant, secant, cotangent. We want to, we're going to have to memorize what these relationships are in a sense, but I think they're going to be easy for us to remember. Remember, you've got SOHCAHTOA to help you remember your primary 3 relationships. The other 3 relationships are always just the the reciprocal of those, not inverse, the reciprocal of each of those, the flipped fraction version of those guys right there. I'm going to do one last bare smidge little thing right here just to kind of help us see one last thing right here. If I were to tell you that the tangent of theta equals 3 and that I wanted you to draw a triangle for me that represents this, part of my dilemma is that I'm thinking of tangent as something like opposite over adjacent, but I don't see that here. It helps for us to always think of every single number that we get out of a trig function as a fraction, because now I can think about this as opposite over adjacent, and that helps me to draw a triangle that has a theta in the corner and has the opposite side being 3 and the adjacent side being 1, stuff like that. So that's just going to be maybe my last little helper thought right there. Remember that any number is itself over 1, and it's very helpful to always think about outputs from trig functions as ratios, because that's really how they're originally defined, right? So I think this one went a little bit long, certainly, but this is probably like the single section of the entire class that we introduced more definitions than any other section. So I do think that this was worth the time that we spent right here. I wanted to do enough examples that it's for sure going to get you through the things that you need to be able to do in the My Open Math homework as well. I think I did that. So I'm going to go ahead and call it a video here. We are going to be picking up next week with we're going to take exactly these ideas and we're just going to expand our minds to apply these exact same ideas to a slightly broader set of situations. Section 6.4, we're going to take just another step. We're going to apply it to an even broader set of situations. What we want to do is we want to bring all this sine, cosine, tangent stuff back to being a reference to a circle rather than a reference to a triangle. And that's where we're going to go in the 2 sections that we're going to cover next week. week. So this is our final video for week 1 here. You should be working on your MyOpenMath homework. You should be hitting me up with email questions. You should be hitting me up with MyOpenMath questions if you got them within MyOpenMath. Send those messages inside of MyOpenMath. You should be coming to office hours if you got any questions that you want to talk about. And again, if you don't like the colors I'm using, hit me up and let me know. I'm happy to change any of that kind of stuff for you guys. So I'm going to close it off right here, and I will see you guys in the email, in the MyOpenMath, in the office hours, or next week. Have a good one.